Now we're going to rely on the wave-particle duality to deduce the form of the main equation of quantum physics, the Schrödinger equation. But before going to this main part, let me ask the following question. Which picture is more fundamental, the particle-based picture or the wave-based picture? So here I have an example of what we usually mean by a particle. In this case, here's a baseball. And this is an object which has a well-defined velocity and position at any given time. We can identify its position simply just by looking at it and measure its velocity. In contrast, when we're talking about waves, it doesn't really make sense to ask the question where the wave is located. So here in this example, I'm showing a wave which is generated using a rope. And well, just by looking at it, you realize that there is no well-defined position of a wave. However, what we can do, we can define the wave velocity and the wave vector. And also we can describe a wave using this mathematical expression. So in this expression, u is the displacement. So in this particular example, u is the vertical displacement, which is a function of the coordinate and time, and the x-coordinate is this horizontal direction. And for a simple sinusoidal wave, this is the kind of expression we're going to get. Now, the relation between the wavelength and the wave vector is lambda, the wavelength, is equal to 2 pi over the wave vector k. And the relation between the frequency, omega, and the velocity of the wave, so the velocity is essentially the coefficient of proportionality between omega and the wave vector k. There are actually two types of commonly used expressions to describe a simple sinusoidal wave, such as this one. So the one I just described, and also the one using this exponential of a complex argument. So I here is the square root of -1. And they are equivalent to one another. So here the equivalence is established by simply remembering that exponential of I times some real constant, let's say x, is equal to cosine of x plus I sine of x. So this is this equivalence in this case is simply an identity. In the future, we mostly will be dealing with this description of a wave in terms of the exponential of a complex number. And oftentimes we're not going to actually see this imaginary part or real part. We're simply going to be describing a plane wave in terms of this exponential. So don't be surprised to see that. Now, going back to the question about which picture is more fundamental, particles or waves, I'm going to make a statement that the latter, the waves, are more fundamental than particles. Because we cannot represent a wave in terms of a particle, but we certainly can represent a particle in terms of waves. And this representation in the mathematical language is called Fourier transform. So Fourier transform, so here is a generic mathematical example of a Fourier transform for some arbitrary function f of x. And in this case, so this a sub k represents so-called Fourier harmonics or amplitudes of this function f of x. And these guys, e to the power ikx, in some sense correspond to a snapshot of a wave at any given time. So by decomposing an arbitrary reasonable function into these Fourier harmonics, we essentially represent it as a linear combination of waves. In particular, what we can do, we can consider, let's say in this case, a function f of x, which has a very sharp peak with some spread out narrow width around this location, let's say delta x. And so if this is our f of x, so we can represent this f of x in terms of these waves, and this would be a decomposition of a particle-like entity into waves. Now, going back to quantum mechanics, we can resolve a dilemma that was presented by the experiments which revealed wave-particle duality. The dilemma being of how we want to describe our quantum mechanical objects, either as particles or waves. And according to the discussion in the previous slides, it seems reasonable to try to describe our quantum mechanical objects in a more general form as waves. And what I have in mind here are the experiments of the type by Davison and Germer, who saw that electrons, when being reflected from a crystalline structure, they exhibit interference-like pattern, just like light would do. If we wanted to describe interference of light, we actually know how to do it because we know how to solve Maxwell's equations. So the solution of Maxwell's equations in vacuum are called electromagnetic waves. And in the case of a free electromagnetic wave, we would simply have written a plane wave, just like in the previous slide. And so this indeed would describe the data in terms of interference of light. Now, having in mind these experiments which established sort of one-to-one correspondence between the interference of light and interference of quantum electrons, we are forced to write a plane wave to describe these quantum electrons. So we're going to write, let's say for free electron moving in the x direction, we're going to write this exponential to the power I kx minus omega t. But without a left-hand side or right-hand side, this is not a legitimate mathematical expression. To make it such, we introduce essentially a new mathematical object, the wave function, psi of x and t, and we in some sense postulate that free electrons are described by this plane wave with some coefficient. It's not very important now, and k is the wave vector of an electron and omega is the frequency of the electron. Now, to relate k and omega to more familiar physical properties such as momentum and energy, we recall the de Broglie relations between them, between p and k and omega and energy. And those relations are the following. So p is equal to the Planck constant h bar times k, and energy is equal to h bar times omega. So we may as well write this wave function for the electron with momentum p as some coefficient e to the power I over h bar p times x minus energy times t. So we sort of postulated a solution to our quantum mechanical problem, but we don't have a problem yet. We don't have a fundamental equation that our wave functions, electronic wave functions, are going to satisfy. So in order to figure out this equation, we can recall the following simple equation, namely the equation for the energy, the kinetic energy of a free particle. And as most of you know, this kinetic energy is equal to mv squared over 2. Or if we want to write it in terms of momentum, momentum is mass times velocity, so we can write it as p squared over 2m. And now comes the main trick in figuring out, or guessing, better to say, a fundamental equation of quantum physics. So first of all, we're going to demand that whatever equation we're going to guess must give this plane wave as its solution. And also we're going to demand that the energy which appears in this plane wave must be related to momentum per this relation. Basically, we must enforce that free electrons indeed have so-called free particle dispersion or free particle spectrum, mv squared over 2 or p squared over 2m. So this also must be satisfied. Well, a reasonable naive guess, and it turns out to be incorrect, let me just say, would be to assume that the electron wave function satisfies the usual wave equation. So let's say in the one-dimensional case, we would write simply d2 over dx squared minus 1 over the velocity of our wave, d2 over dt squared, psi equals to 0. Now, if we plug either of these expressions in this equation, and you can check it as an exercise, we're going to get the familiar relation between the frequency and the wave vector that I wrote in the previous slide, or the analogous expression for the energy and the momentum. But it would work for electromagnetic waves. It would work for photons, which are quantum electromagnetic waves. but it does not manifestly work for electrons, because this linear relation between the energy and momentum is not the kind of relation we're looking for. So we must construct some other equation. And the simplest such equation can be constructed. Let me just erase this part here. So the simplest such equation can be constructed if we notice that the derivative, if we apply, let's say, the time derivative to this plane wave function psi, it's going to give us the same wave function, but multiplied with minus I over h bar times e times psi. So this is essentially the result of the action of this time derivative, and for the spatial derivative we're going to get plus I over h bar p times psi. So this is the action of the x derivative. And so we find here a clear correspondence between the energy and the derivative h bar d over dt, the momentum, in this case one-dimensional momentum, and minus I h bar d over dx. And of course, if we were to have a three-dimensional momentum, a momentum vector, we would need to write minus I h bar gradient. Let me write it like this. So this nabla is called gradient, which is if we have a function, let's say f is by definition df over dx, the unit vector in the x direction, df over dy, unit vector in the y direction, plus df over dz, unit vector in the z direction. So if we want to enforce the constraint that the energy of the particle E is equal to p squared over 2m, so we sort of forced to construct the simplest equation that would do it in the following form. So in let's say in the left hand side we're going to write our energy and E I h bar d over dt acting on the wave function psi, and in the right hand side we're going to write this so-called momentum operator. Let me actually put a hat here, p squared over 2m, also acting on psi. Now if we write it explicitly as a mathematical differential equation, I h bar d over dt, p squared over 2m will follow from here. So I squared gives us minus 1, h squared is h squared, and this gradient squared is called Laplacian. So it's just the usual notation for this Laplacian, as is either this gradient squared explicitly or this triangle. So moving this p squared over 2m to the left hand side, I can write it as plus h squared Laplacian divided by 2m, and this whole thing acts on the wave function, which in the three-dimensional case is a function of the position, three-dimensional position r, and time t. And this equation is the free Schrödinger equation, which we sort of derived. But of course we should use the word derived in quotes, because there is no way we can derive a fundamental law of physics, and the Schrödinger equation is an example of such a law. So our derivation is nothing but a guess, but it's a very convenient guess because it allows us to generalize this equation to a very important class of problems, namely to the problems where the electrons are not free electrons but move in the presence of a potential. So to see how this happens, let me sort of identify the right hand side of this equation in this form with an energy operator, so which is called in quantum mechanics is called Hamiltonian. So this operator h hat is a very important object in quantum mechanics. Let me actually write it. It's a Hamiltonian. And in the case of the free particle, it is simply this kinetic energy, but it's very natural to generalize it to the case of an interacting particle or particle in the potential, in which case I will write p squared over 2m, the kinetic energy, plus the potential energy V of R. And if I do so, and if I write the resulting equation as I h bar d psi over dt in the left hand side, and in the right hand side is h hat psi, so this actually becomes the fundamental equation of quantum physics that actually appears on the logo of our course, and which quite amazingly contains just about all of non-relativistic, single particle physics, and it can be generalized also to describe many particle physics. So the theory of metals, theory of superconductors, pretty much everything we can imagine that doesn't involve relativistic effects is contained in this equation.